Hello everyone. Today we're going to talk about trigonometric substitutions, which is another technique in your tool belt for evaluating integrals. So it says here that to evaluate integrals involving the square root of a squared plus x squared, the square root of a squared minus x squared, and the square root of x squared minus a squared, it sometimes helps to make what's called a trigonometric substitution. And I should mention that a here is just some constant. So this could be the square root of 9 plus x squared, as an example. Already starting the video with a mistake. Alright. So I think the best way to figure out what trigonometric substitution is to just jump in and do one. So let's look at example 1. Here we've got the integral of x squared over square root of 9 minus x squared dx. And just as a reminder, if the dx is on the top, that's okay. It's the same thing as writing the dx over to the right. Just a shorthand notation for it. So what we're going to do is, first off, note that regular substitution doesn't help here. If we try to let u equal 9 minus x squared, the du would be negative 2x, which is not what we see next to the dx. So if you try a regular substitution, it doesn't quite work out. So let's give this new trigonometric substitution a try. And here's what we're going to do. We're going to let x equal 3 sine theta. Now, most of the time, we don't let the variable that we already have equal something else. Usually we let u equal some part of the expression here. So it's a different kind of substitution. Alright, so we have x equal 3 sine theta. So dx, the derivative, would be 3 cosine theta, d theta. And we're going to make one little note here, which is that theta is between negative pi over 2 to pi over 2. What this does is it forces the sine function to be 1 to 1. So let me just write that over here. So forces sine to be 1 to 1. There's my shorthand for 1 to 1. Which is going to help us down the road when it comes time to finding the inverse trig function, or getting it, I should say. It's also going to help us when we're evaluating the square root of cosine squared, which we're going to come to in just 1 second. Alright, so with this substitution, let's go ahead and replace all of the x's with 3 sine thetas. So we have the integral of 3 sine theta quantity squared over the square root of 9 minus open paren 3 sine theta close paren squared. And then remember that the dx gets replaced with 3 cosine theta d theta. So let's do that right here. 3 cosine theta d theta. It's a common thing to forget to do with these problems, so just make sure to take note of that. Alrighty, we've got now a radical on the bottom that can be simplified. So this is actually the key part of the trigonometric substitution method, which is to take that radical and collapse it down so that you don't have the radical anymore. That's really the key part of trigonometric substitution. So let's work on that radical. Change over to gray. Oops, I already did that. So we got square root of 9 minus, and if we take the 3 sine theta squared, we'll get 9 sine squared theta. Now we can factor out a 9. Oops. Fix that. Hey, okay, there we go. And then simplify even more by using the Pythagorean identity, which says sine squared theta plus cosine squared theta equals 1. If you solve that for cosine squared theta, you would get 1 minus, well, you get cosine squared theta equals 1 minus sine squared theta. So we can replace 1 minus sine squared theta with cosine squared theta. Now at this point, when we take the square root of 9, we'll get 3. When we take the square root of cosine squared theta, technically it's the absolute value of cosine theta. But since up here we already forced theta to be between negative pi over 2 and pi over 2, where cosine theta is positive, think about that, that's in the first quadrant and the fourth quadrant, then the absolute value bars around the cosine theta wouldn't do anything. They don't do anything when the inside number is a positive number. So this next step that we're going to take is because theta is between negative pi over 2 to pi over 2. We can drop those absolute value bars, which is great. Alright, so coming back over to our integral, what do we have here? So we have 9 sine squared theta over, and then this whole radical right here, through these steps that we took, collapses down into 3 cosine theta. 3 cosine theta. We'll copy down the rest of it. All right, scroll down a little bit. Now, we can simplify in the radical. Choose a nice red here. Is that a good red? Ah, good enough. So the 3 cosine thetas cancel, and we just end up with the integral of 9 sine squared theta d theta. And this is a trig integral, so it's a trigonometric integral. It's one that just has some trig functions inside of it. And 7.2, the previous section, is where we talk about how to evaluate integrals like this. So the trick here, when we have sine and cosine as even powers, taken to even powers, what we do is we lower the powers using the power lowering formulas. So here we'll lower the power of the sine squared, and we might as well pop out the 9 as long as we're at it, by writing 1 minus cosine 2 theta over 2. So this is the power lowering formula for sine. It takes the sine squared and converts it into a cosine to the first power. This 2 right here is just in front of the theta. It's a coefficient in front of theta. It's not an exponent. So we took the exponent of 2 and brought it down to an exponent of 1, which makes things much easier to integrate. Alright, so continuing on, we can pull the 2 that's on the bottom of the fraction out to be with the 9. So we get 9 halves. And then when it comes to integrating, remember that we're integrating with respect to theta. So when we integrate 1 with respect to theta, we just get theta. There's theta. When we integrate cosine, we get sine. But there's a 2 in front of the theta here. So by either thinking about it with a mental substitution, letting u equal 2 theta, or thinking about it as the reverse of the chain rule, we've got to have an extra factor of a half right here in front of the sine 2 theta. So then if we think about taking the derivative again of 1/2 sine 2 theta, we'll get 1/2 cosine 2 theta times the derivative of 2 theta, which is 2. And that 2 cancels off the 1/2 to just give us cosine 2 theta. So you can always double check your work there. Alright, so now we have our antiderivative in terms of theta, but what we want to do is we want to go back up to x, the original variable that we started out with. And there's a bit of a problem. We can definitely solve x equals 3 sine theta for theta, and we'll do that in a moment. But we are going to have a harder time with sine 2 theta. Like, we can get all of the trig functions at angle theta. We'll know anything about angle theta. But angle 2 theta, we don't really know too much about. So what we're going to do here is break the sine 2 theta down into trig functions that have an angle theta in them, because we're going to know all about angle theta. So the way we'll do that is by using a double angle formula. Let's do that off to the side here. Remember that sine 2 theta is 2 sine theta cosine theta. So that 1/2 sine 2 theta is going to be just sine theta cosine theta. All right. So now we've got 9/2 theta minus sine theta cosine theta plus c. Almost there. So now what we have to do is, again, our goal is to get from thetas back into the original variable, which is x. So let's go ahead and write up the relationship between those two variables. Remember that, so the next step, remember that x equals 3 sine theta. So solving for sine theta, we get sine theta equals x over 3. So what we can do is draw a little triangle off to the side with the angle theta in it, such that sine of that angle theta is x over 3. So we'd have to have the opposite side as x and the adjacent, the hypotenuse is 3. Now we can complete this triangle by writing what the adjacent side would be using the Pythagorean theorem. So this is going to end up giving you the square root of 9 minus x squared, if you use the Pythagorean theorem on that. So now we can get any trig function at angle theta we want. We can get tangent, that would just be opposite over adjacent. We can get cosine if we need it, adjacent over hypotenuse, any of them. And what we need actually here is sine theta, which is just x over 3, either from the triangle or from sine theta equals x over 3 right here. And cosine theta, which we just mentioned, we can write adjacent over hypotenuse. Now the only last thing is we're going to have to replace theta, and to do that we can just take the inverse sign on both sides of the equation sine theta equals x over 3. So what we can write here then is, let me make sure I got blue. So what we can write here is 9/2 inverse sine x over 3, and then the sine theta we said was x over 3. The cosine theta we said was the square root of 9 minus x squared over 3. Close paren, put a plus c. And then maybe the only last thing to do here would be to clean it up. So we could maybe distribute the 9/2. So we have 9/2 inverse sine x over 3. I'll go ahead and put parentheses around this just to make sure that we know the x over 3 is inside of the inverse sine. And then the 9 on the top of the 9/2 will cancel with the 3 times 3 on the bottom of the fractions when it distributes. So all you'll have left would be 2 on the bottom. So you'll have x times the square root of 9 minus x squared over 2 plus c. All right. So that's example 1. I'll just finish this off by talking a little bit about what kinds of substitutions. I mean, we just started off by saying let x equal 3 sine theta, but how in the world did we get that? Well, what it came down to was we needed that radical to collapse, and at the core of it we had 1 minus sine squared theta equal to cosine squared theta. That's what allowed the collapse from 2 terms down to just 1 term. Now the other Pythagorean theorem, Pythagorean identities, like tangent squared theta plus 1 equals secant squared theta, and identities like that are going to have their own ways of collapsing. So for example, if you do have the square root of a squared plus x squared, if you replace the x, let me just do a little bit of writing here. So if you replace the x with a times tangent theta, notice that what you'll be able to do is take an a squared out. Oops. A squared, and you'll be left with 1 plus tangent squared theta, which by a trig identity gives you secant squared theta. 1 plus tangent squared theta is equal to secant squared theta, or tangent squared theta plus 1 is secant squared theta. So then the square root can apply to these the a squared and the secant squared theta, and you'll just get a times secant theta. So it collapses the square root. So we already saw that with the square root of a squared minus x squared, you can let x equal a sine theta. So just going back up to our example, it was the square root of 9 minus x squared. 9 is like 3 squared, so that's why we put a 3 right here in front of the sine theta. And that helped us collapse the radical. So for the square root of x squared minus a squared, you'd want to let x equal a secant theta. The restrictions for theta over on the right help you not only drop the absolute value, but also help you find inverse trig functions later on down the road. And lastly, one question that some people ask is, couldn't you use, for example, cosine theta instead of sine theta here? Wouldn't the collapsing work exactly the same way? And the answer is yes. You could use a cosine theta if you wanted to, instead of a sine theta, and it would work exactly the same way. At the end, your answer might look a little bit different, but ultimately it'll be the same answer. You would be able to, if you took enough algebra steps and used enough trig identities, you'd be able to get from your answer to this answer that we got here. So that's it. That's the first example of trig substitutions, and the kinds of substitutions that you would want to make. Oh, one last thing before we go. A quick mnemonic to remember the square root of a squared plus x squared, that the substitution you want to make is a tangent theta. The plus in the middle, kind of reminds you of a t. And so when you see that plus in the middle, that can kind of remind you of the t in tangent. And then a terrible mnemonic, so that's a good mnemonic, I think. A terrible mnemonic for the other parts is if you see the a squared minus x squared versus the x squared minus a squared, if you think of a and x as spelling axe, then you can say it's a sin to axe my professor. So there's a mnemonic for the second one. Take it or leave it. Thanks for watching this video, and see you in the next part.